In this video, we will continue to examine the structure of neural networks, starting with the concept of a perceptron. Multi-layer perceptrons are an early simple structure of neural network model. A perceptron can be considered the simplest component of a neural network. Neural networks were designed after simplified versions of the structure of neurons in the brain. And within this, they have a set of inputs that feed into a single output by taking the weighted sum of those input values. Perceptrons take the weighted sum and then apply an activation function that transforms the output or the kind of aggregation of those into a different functional form. In the context of neural networks, there are a range of activation functions that are commonly used. So let's take a moment to look at a few common ones. So an identity function is sometimes used in these neural networks, which is effectively the equivalent of applying no activation function. This would result in a linear output from the respective node. So if we wanted to emulate a linear regression model, we might use this identity function as the activation function for the perceptrons in our model. A sigmoid function, shown on the right here, follows this S-shape, similar to a logistic regression. And in that way, it's also similar where the output of the activation function is bounded between 0 and 1. This type of activation function, for this reason, is often used in the output layer of a model, that is the last layer of our neural network, especially when the goal is to classify a binary dependent variable. But sometimes these are used in other layers of the network as well, which we will talk about a little bit more later. The tanh activation function is another commonly used activation function in neural networks, as it follows a similar functional form as sigmoid functions, but is instead bounded between -1 and +1. This allows for both positive and negative values to be propagated through the network. And don't worry, we're going to revisit this idea of data propagation shortly. Linear rectifier, or ReLU, activation functions are also quite common. These functions are 0 when the input is less than 0, or when the input is summed and becomes less than 0, and then it's linear for input values that sum to values greater than 0. So in this way, the activation function helps to create filters within the neural network such that only some nodes activate under certain conditions while other nodes might remain dormant. Finally, the softmax activation function can be thought of as an extension to the sigmoid function, but is commonly used in the output layer when your goal is to predict a dependent variable with multiple labels, as opposed to just having a binary label. The softmax activation function will result in a probability distribution across all of the nodes in the respective layer, where all outputs across the nodes are between 0 and 1, and also sum to 1 across that layer. By arranging multiple perceptrons into 3 or more layers, we then arrive at a multi-layer perceptron. These are also sometimes described as feed-forward neural networks, again, another form of deep learning, in that the flow of data is fed or propagated to each layer sequentially. So when we look at a neural network model, we can describe this flow of data, again, as propagating from the input, or the bottommost layer, to the output layer, that top layer, through additional hidden layers. So those layers in the middle between the input and output are considered hidden layers. Of course, sometimes neural networks will be depicted horizontally as opposed to vertically as in this example, but the flow of data still remains the same, going from input through hidden layers to the output. In this case, the input layer represents the raw features that we have to include in our model, and the output layer produces a prediction for our dependent variable. We can also recognize that each node in a given layer is the result of a regression using all nodes in the previous layer as input. So the hidden layer is really just the result of multiple regression outputs using the preceding layer. So no matter whether we have a model structure that looks like this, Or if we have something much more complex, each node is effectively the result of a regression. But you may be asking then, particularly within the hidden layers, what is it that these are regressing on? Our dependent variable isn't really introduced until the final layer. So in a neural network model, we can think of all of the hidden nodes, all of the hidden layers, as regression models that are trying to learn optimal ways of constructing features from the preceding layers to best support a prediction for the dependent variable. Through all of the hidden layers, the model is learning how to transform, combine, and aggregate all of the inputs from the preceding layers to create a set of features in the penultimate layer that can then be used to predict our dependent variable.